on the mathematical rather than the conceptual side, why do we seem to have multiple sort of best mathematical models of causal learning? So I think this is painting with a broad brush, but over the last 20 years, there have been a number of different theories that people have come up with for causal learning, and I'll be focusing primarily on sort of learning from cases or evidence, what sometimes is called causal inference, in contrast with causal perception, where you see things happening. And the mathematical theories, I think, that people have developed, one of the challenges is we're not seeing, in my view of the literature, we're not seeing what we see in many other disciplines, which is, or many other areas even of psychology, where we see a sort of steady improvement in the quality of the models. Instead, we seem to frequently have almost intractable conflicts where we have multiple mathematical models that seem to make sense of different data sets. So what I'm going to sort of try to claim today, we'll see how this goes, is first I want to argue that on purely mathematical grounds, there actually is a privileged functional form for the kind of limit of what you should believe in the long run, essentially about expectations. This is mathematically privileged in the sense that from a very, I think, simple and intuitive set of assumptions, there is one unique function that we should use in terms of representing causal relations of a particular type. In fact, this mathematical form, this functional form, when you look at the special cases that correspond to plausible experimental designs, what you actually find is that what comes out are the different models that people have proposed as special cases of this single privileged functional form, which suggests that perhaps what's going on is we don't actually have multiple best mathematical models. Rather, what we have is we've got, in some sense, people learning appropriate functional parameters depending on the context in which they find themselves. And so it looks like people are doing different things, but actually it's the same thing in special case versions of it. Okay, so that'll be the sort of positive, hopefully good, warm, fuzzy feelings part of the talk. The last part of the talk is going to be to say, but the problem is I think that only works when we're looking at the population level, when we're looking at expectations and these kinds of things. I'll then present some reason to worry that, in fact, we are still completely in the dark when it comes to what is happening at the individual level of causal learning. Okay, so it's a lot of high level. Let me dive into the details because I know that time is limited. So let's start by thinking about perhaps the easy case, the one that I suspect many of you in the room there have already been thinking about, in some cases for even longer than I have. And that is just suppose all the potential causes and effect are binary. There's a long history of arguing that on both metaphysical and mathematical grounds, if all of the potential causes are generators, that is, they can produce the effect, they don't block the effect, then the right functional form is to use the noisy or. Here's just one particular expression of it. If you have generators and preventers, right, so some causes reduce the likelihood of the effect, then it's the noisy or and. Actually, noisy or, not and, NAND gate. But hopefully these equations are familiar to many of you. Interestingly, one of the things that I think is perhaps not as well known in the psychological cognitive science community is actually for now almost 20 years, we've known that these are the normatively privileged functional forms for under very, very general assumptions about how causation might work. If you have binary causes and effects, Fabio Cosman proved that these are the unique functions that satisfy these very general assumptions. Okay, so this has been known for a while. I think that there sort of is this, if you've got binary causes and effects, this seems like the right way to think about how causes ought to work. And then, of course, there's a question of whether that is actually how humans think about it. But of course, the restriction to potential causes and effects being binary is a pretty strong one. The vast majority of things we encounter in the world are not binary causes. They're not on-off. They are rather continuous in form. And so that raises the question, can we give a privileged functional form in the general case? So what the first thing we find is that when we think about this, we discover there's a couple of ambiguities. So the first ambiguity is that in the binary variable case, we almost always use 0 both to indicate the baseline, which is to say the state of the effect if there were no causes around, and we use 0 as the lower bound, which is if all you have is preventers, you're sort of kept at 0, but you can't go below 0. They're binary after all. There's only 2 states. Now, this ambiguity is not a problem when we're in the binary case, because mathematically you can move things around so that you can, if you say, no, I want 1 to be the baseline, okay, that's no problem. We can flip that around pretty straightforwardly on the mathematics. But when we have continuous variables, we no longer are able to have this ambiguity, right? This ambiguity creates problems in terms of how we think about what the roles or the possibilities are for the factors. The second ambiguity is that there's a distinction between what we might think of as reducers, things that reduce the value of the effect, and those that block the influence of some cause on the effect. Now, again, in the binary case, these two amount to the same thing, right? Something that would reduce the effect from 1 to 0 is not any different, given that 0 is the baseline, from something that blocks a cause influencing, right? So mathematically, these are not distinguishable in the binary case, but obviously they are distinguishable in the continuous valued case. It's something that reduces the value of the effect is different from something that blocks the influence of other causes. Okay, so what we need to do is draw a couple of quick distinctions before I get to the theorem on the next slide. The first is that I'm going to use 0 as the baseline and say, look, there can be some lower bound, could be negative infinity. There could be, and then there's some upper bound, could be positive infinity. Okay, so I'm going to be treating all the causes and effects as continuous variables, but with 0 as the baseline. And of course, that's, we can mathematically transform anything to make 0 its baseline. We can talk about the metaphysics of that if people want. Of course, 0 could be equal to L, right? The lower bound could be the same as the baseline. Or U could be 0, right? We could have the upper bound is actually the baseline, and all we can do is have things get worse from where they are or get more negative from where they are. The second thing is we have to separate out that should have been reducers, right? Reducers, preventers, you can think of things that are lowering the value of E, and blockers. Okay, so those are now going to be two different notions of negative causation. Right? So there's still generators that increase the value of the effect, but now there are sort of the opposite of generators. There are things that lower, reducers, that lower the value of the effect. And there are things that simply say causes don't have effect, right? That block the influence of causes. There's two different ways that we can have negative impacts in the traditional sense. All right, so given that, we need to make some assumptions. Here's some very simple ones. I'm not going to go into detail on these. Basically, these just say whatever the function is by which the effect is produced from the causes is obeys sort of very natural, simple mathematical properties like symmetry, right? The order in which I list the causes doesn't matter. Determinism, that given the set of causes, the impact on that multiple different settings for the causes can lead to the same probability of the effect, right? So many-one mapping. There's a couple more assumptions we need to make that are a bit more contentful, right? So the first is we're just going to assume that if everything's inactive, then E is at its baseline. Feels like a pretty safe assumption. That it almost seems definitional of baseline. We're going to define causal strengths in terms of their expected change from baseline. So that's a kind of very weak notion of modularity, essentially, that says that things are additive rather than interactive. And that if everything is, at its maximal state, then the effect is at its maximal state, which is also a kind of natural intuition, I think, because it seems weird to say that the variable could go to some bigger value, but there is no way to get it there. Okay, so these are contentful assumptions, but again, fairly, I think, minimal ones about the nature of causality. And it turns out that those assumptions alone, plus the assumption that the causal function is a finite polynomial, could be arbitrarily large degrees, but it has to be a finite polynomial, then this is the unique expectation for the effect as a function of the generators, the reducers, and the blockers. Okay. I'm not going to try and unpack this math. It is 9:54 in the morning. There's no way anybody wants to be having me unpack this equation. You'll notice, though, that it does bear a certain similarity to the noisy or and. You're sort of normalizing various things, but it has that flavor to it. So in that sense, it shouldn't look too unfamiliar. I'll also give a conjecture, which is that you might worry about that assumption that the causal function has to be a finite polynomial. That seems like sort of this strange technical assumption that you might object to. There's actually a pretty weak smoothness function, smoothness condition that we could use instead. And that I conjecture that this function is also the unique privileged function, but haven't been able to prove it yet. Haven't been able to prove the counterexample to it, but haven't been able to prove it yet. So I think that this holds even under a very weak smoothness condition rather than the particular one of finite polynomial, but there we are. I'll also note, of course, finite polynomial is actually a pretty weak condition. There are an enormous number of things that are expressible as a finite polynomial, or at least approximatable as. All right, so you might say, so what? That's a whole lot of math. Why did we go through all of that? What's the interesting thing? Well, the first thing is, I alluded to the similarity to the noisy or noisy and structure. And in fact, if the lower bound is 0, right, so the lower bound and the baseline coincide, and the upper bound is 1, and every cause is either a 0 or 1, then you get out the noisy or and. Okay, so the special case of binary variables ends up giving us exactly what we would want, right? So that's kind of almost sanity check that this is making sense as a generalization. So one way to think about this, you might say, is as a generalization of noisy or noisy and. The more interesting thing, though, is that we can use this and we can ask about other kinds of special cases. So I want to just highlight one here that I think is of particular relevance, which is, suppose that the lower bound is negative infinity, the upper bound is positive infinity, and all the causes are binary. Okay, so the causes are present or absent, but the effect ranges from negative infinity to positive infinity. Okay. Now, in that case, let's also just suppose we have no blockers. So we only have reducers and generators, right? We have to distinguish that because now the effect ranges across more than just the binary values. Well, there now the expectation is what you see here, which is basically the weighted by the weights times the causes, that difference. Okay. So sort of additive, just sum of the weights. Now you might say that seems kind of odd. Why is he singling out that particular one? The first thing I'll say, by the way, I should also say, by the way, you might be worried because I've got negative and positive infinities, and you can see there's lots of things in the functional form where it's infinity divided by infinity. It all works out. I won't go through the derivations here, but all of the things sort of cancel out to make everything nice in terms of this expectation, this reduction. But the thing that's important here is this is actually the same thing as the classic conditional delta p. It's the same long run that is the stable equilibrium of the Rescorla-Wagner and classical conditioning models of that type. Okay, so what this is actually saying, if you're a fan of conditional delta p or Rescorla-Wagner and its various variants, that in fact that also comes out of this functional form. The only difference between noisy or and this linear sum is whether we assume that the effect is bounded at 0, 1, or the effect can range from negative infinity to plus infinity. Simply change your assumption about the range of the effect variable, and you flip between what I would argue are the two dominant theories of causal inference, at least at the current time, and the things that seem to give pretty good model fits. I've got an additional conjecture here, which is you might worry that I'm talking only about expectations. For simple cases, we can prove that actually you can give a step-by-step conditional probability update, sort of like a Bayesian update that obeys all the things you would, that is also uniquely privileged and that looks like Rescorla-Wagner generalization of a Skorla-Wagner and then negative infinity to plus infinity, and the generalized dynamic update to causal power for the noisy or and case, right? So it looks like what we may have is a way of capturing and expressing these different theories of causal learning as special cases of this privileged function, which raises a natural question. A natural thought you might have is, well, wait a second, if all that matters is the range of the effect, then we should be able to use essentially exactly the same experimental materials, except tell participants, oh, the effect is bounded, is only 0 or 1, or we tell the participants the effect ranges from minus infinity to plus infinity. And that we should get diverging behaviors in the form of the former group responding as if they're estimating parameters in a noisy or and the latter group estimating in conditional delta p or linear differences in this case. Okay. So there's very natural experiments that could actually test this idea that things are special cases of a privileged function. Between the pandemic and moving institutions in the last few years, I haven't yet had the chance to test that, so I can't give you that experimental data. Okay. So I think that there's at least the possibility of thinking about causal learning as much more unified and much less pluralistic than we might have thought, at least from the mathematical perspective. All right, now let me throw some cold water on that optimism, because everything that I've been talking about and that people have done experimentally around things like noisy or and have almost all focused on group level. So what is the average rating provided across a population? And so that raises the question, well, but what are people doing at the individual level? Because we all know you can have group level behavior that is well described by a function that describes no individuals within that group, right? So there's no necessary connection between the group level description and the individual level descriptions, even if all the individuals are uniform, right? There are connections, but it's not a nice, clean one-to-one. So we actually did something to check on this. We did what in machine learning is sometimes referred to as a bake-off. So we have a whole bunch of different theories of dynamic learning, dynamic causal learning, and we're going to just test them against a whole bunch of individual learning trajectories to see which dynamic learning equation does best, right? That's the notion of a bake-off. Everybody does their best, and we see which one is the best of those. So we fit a bunch of different data, 2 different experimental data sets, one with 50 participants, nearly 200 judgments per, and one with 40 participants, 200 judgments per. So these are, 200 judgments is enough that you can actually get reasonable discrimination between the models. We've got a total of 91 participants. It's not huge data, but it's not bad. And we're just going to try and find the best fitting parameters for each of the participants and for each participant sequence. So, let's even allow for pluralism within a participant. When we deal with these dynamic learning equations, the exact number of parameters is sometimes unclear. So we just use sum of squared error for model fit. It's just a very simple, I understand it's a very blunt, crude instrument for doing model fit because it doesn't correct for the model complexity. On the other hand, model complexity is actually not well defined or not clearly defined for some of these models because they have multiple parameters that depend on one another, right? So it's not simply counting up the parameters. That's not a good measure of the degrees of freedom of the model. So we're just going to use the blunt, crude thing, and we'll just see, right? Of course, recognizing that may reward more complex models. So the first thing to say is we actually did find diversity. Don't worry too much about what this is, but each cluster is a different dynamical equation, and the bars are showing you how many participant sequences were well fit or were best fit by that particular one, right? So we're seeing roughly 4 different kinds of things that we see some evidence for. There's some diversity, but also some things are more popular. But the thing I want to end on is the depressing note that what we found is actually that the best fitting models are almost always, were often bad. So what do I mean by bad? Let's just take a very simple characterization. We'll say that a model is reasonable if the average error is less than or equal to 5. The ratings are on a -100 to +100 scale. So that doesn't strike me as unreasonable to say, let's just have the average error across the, say, 80. Suppose this is an 80 sequence judgment, that across these 80 sequence judgment, the best fitting model should have an average error of less than 5. If we're not even getting that close, that worries me that it's just not a very good model. For the first data set, we had reasonable fits for less than half of the participants, and for less than half the conditions. For the second data set, it was usually less than half. There was one particular condition that seemed to be a bit easier to find model fits for. And moreover, we got evidence when we looked down in more detail that we really do seem to have participants using multiple methods. The unification trick doesn't seem to work very well, didn't model people particularly well, even when we tried to do that. So I know I'm coming to the end of my time. I'll just say, so I think I think the first thing is that hopefully I've started to pique your interest that there really is a privileged mathematical function for causal inference, in the sense of a mathematical function of how the causes combine to produce the effect under very weak assumptions, a unique privileged one, such that we might make sense of human causal learning as estimating parameters within that. If we think that way, then widely used population level models of causal inference end up being special cases that naturally invite a certain kind of experimental test. But we need to recognize that lots of success at the population level is not necessarily translating down to individual level success. And I think that's a place where there is enormous need for mathematical and theoretical innovation in causal learning right now, is to move down to what are the individuals doing, noisy as they are, can we make more sense of what's going on at the individual level? So with that, I will say thanks, and I think there's 5 minutes for questions.
Awesome. Thank you, David. Check that.
Let me know if you can hear the questions.
Yeah, can you hear me?
Yes, I can.
Given the various things that Lauren talked about a minute ago, it strikes me that your simple assumptions, symmetry, commutativity, associativity, and so on, may be simple, but overly strong. And I can think of all kinds of cases that those would be violated. I'm thinking of things like, for example, causes at different time scales trying to be combined somehow, and so on and so on. That's just one example. But so those assumptions that you started with seemed rather strong.
That's a fair question, and I'm making a guess here. Was that Rich Schifrin?
Yeah.
People's voices are more distinctive than they realize. Hi, Rich. You're right. They may be stronger than I want to believe. I think if we start from one thing that I think is important is that this approach, and maybe I should have been clearer about this at the outset, there's a certain amount of starting with the assumption of a at least somewhat modular causal world, that we don't have a dense interwoven causal nexus of interactive causes such that nothing can be separated out from anything else. I think that many of the cases that concern philosophers, and myself included, when I think about the metaphysics of causation, we often focus on what we might think of as edge cases where our intuitions start to break down. But that to me actually suggests that perhaps human causal cognition is, at least starts with the presumption of a kind of quasi-modularity. That may be wrong, but I certainly should have been clear. I think the assumptions are simple relative to the idea that we're trying to understand the world as a quasi-modular causal network. Fair point.
Yeah.
From a scientific perspective, if you're doing a big meta-analysis trying to understand what impacts a certain effect, you have say trials that come out of your theory that basically talks about what the regression coefficient might be or what they should look like.
I'm not sure for the second part of the talk, you mean?
So, I mean, in general, if you're trying to understand what the causal structure is in the world out there, and you're doing a big meta-analysis instead of fitting a regression and trying to interpret the coefficient, right? ideally these coefficients could be anything, but based on your constraints, it seems like there's a certain functional form which works well with him. Is
Yeah,
that-
well, so I think there's a couple different things. So this approach does assume that there's a single causal structure. So one challenge is, and so differences in regression coefficients should be driven by, for example, differences in the background context that could be modeled. I think that the challenge in a lot of meta-analyses is that we actually have different causal structures in different parts of the world. So we're trying to fit something that may not, may be more heterogeneous than we want to allow. Again, I'm assuming a kind of homogeneity here. So, this was very driven by a lot of the human cognitive literature and less about the machine learning work on causal discovery. It would be interesting to try and take this privileged function and see how well it could work on some canonical causal discovery data sets. I agree.